In this video, we're going to talk about the wave nature of light. So what we mean by the fact that light is basically like a wave, but also can be like a particle. And then also we're going to review and talk about electron configurations. So first off, just to review what we've discussed in previous weeks. So the Bohr model of the atom. So we talked about several different types of models of the atom, but the Bohr model is what we pretty much accept for the most part, because it represents it most accurately, at least until we get into quantum mechanics. But Bohr talked about the electrons orbiting in fixed energy levels. So we had these different energy levels here. So there's an energy level. This is the first energy level, and then this is the second one, and then this is the third one, and then they go out further, 4, 5, 6, etc. And then the electrons are only found in these specific energy levels and nowhere else. So we talked about how you can't have an electron that, for example, is this far away between the nucleus and the first one, and you can't have an electron that's somewhere between energy level 1 and 2. It's either in level 1, or it's in level 2, or it's in level 3. And then we use the word quantized to express that fact that you can't have an electron that's somewhere between energy levels. It's only on a specific energy level. We're using the word quantized for that. And then we also talked about the actual names for these. So on the 1s, so the first energy level just has one sublevel, and we called it 1s. And then the second one has two sublevels, so 2s and 2p. The third one has three of them, 3s, 3p, and 3d. And then the fourth one would have a 4s, a 4p, a 4d, and then 4f. And then the fifth one theoretically has 5. All of that fifth sublevel is never even used, so we don't have a real a letter designation, if you will. But we talked about how these two are very, very similar in energy level. So this 2s and 2p together, those are two sublevels, and those comprise the second level or the second energy level. And then we talked about how the different, so these letters, S sublevels, whether it's 1s, 2s, 3s, and so on. S sublevels can only hold 2 electrons. P sublevels, whether it's 2p, 3p, 4p, etc., those can hold 6, because there's actually, and I have it on the other slide, so I'm getting ahead of myself already, but there's 3 different orbitals, and then you can fit 2 electrons in each one, and then 2 times 3 is 6, so that's where the 6 comes from. And then the D, so whether we're talking about a 3D, a 4D, a 5D, etc., those can hold 10. And then F, which you only see with the lanthanide and actinides, those can hold 14. But the maximum number of electrons you can have in a level is by adding all those up. So for example, if we're talking about the third level has 3s, 3p, and 3d. S orbitals can hold 2 electrons. The p sublevel can hold 6, and the d sublevel can hold 10. So what they mean by this, the maximum number of electrons per level is obtained by adding. So you just add 2 plus 6 plus 10, and we get 18 electrons total can fit on the third level. And then I believe we also talked about these different shapes. So, what does S, P, and D and F really mean? So the S is referring really to the shape of the orbital. So all of these S orbitals, they have this spherical shape. And if you want, you can think of, S is for spherical. That's not what it actually stands for, but that's kind of one thing that I think helps. But we call these orbitals. So orbital is the same thing, pretty much, as sublevel. But an orbital is the region of space where there is a very high probability of finding an electron, and it's about 90%. I think the book may say 95%, but the point is that in this 3s, for example, you have a 90% probability of finding the electron somewhere in this sphere. And outside the sphere, there's just a really, really low probability of the electron being there, but it could be there. And when we solve really we're solving like the Schrodinger equation. And if you were to go on to university and major in chemistry, you would take a class called physical chemistry. And in that class, you actually learn about the Schrodinger equation and the Heisenberg uncertainty principle and all that fun stuff about quantum mechanics. But when we solve those equations for the 3s level, we get a shape that looks just like this. So that's how we know that they are these shapes, because we're solving these mathematical equations. And we just assume what's the shape if, for 90% probability, and that's the shape that we get. If we increase the probability to 95, it would still be spherical, it would just be a little bit of a bigger sphere. But that's kind of getting into quantum mechanics, but we want to stick to fundamentals. But just one thing that's important from this slide is, all the s orbitals are spherical, and then as you get from higher energy levels, so going from 1s to 2s to 3s, the orbitals get larger. And the electron, on average, is further away from the nucleus. So an electron in a 1s orbital is on average closer to the nucleus than an electron in a 3s orbital. And an electron in a 2s orbital is on average farther from the nucleus when you compare it to an electron in a 1s. That's the important thing. So that's what this bullet point is referring to. That's an important takeaway from this slide. We also looked at the p orbitals. So they're these dumbbell shapes, and this is just what it happens to look like when you solve the Schrodinger equation for, a 2p in the x dimension, for example. It just happens to have these two lobes, so we call these lobes. That's just what it looks like. And then we have three of them. So we have one in the x direction, one in the y direction, one in the z direction. And if you overlay all of them, you get a picture that looks like this. And it's still just two electrons. So the same rules apply for s and for p and the others. For each orbital, you can fit two electrons. And the p sublevel, we've got three different orbitals, one in the x direction, one in the y, and one in the z, 2 electrons each. 2 times 3 is 6, and that's how we got the fact that the p sublevel can hold 6 electrons. That's again, that's where that 6 comes from. So they all have the same shape, but they're oriented along different axes in space, x, y, and z direction. And the D's, same kind of thing, but just now we have 5 of them, and they all are kind of like a little clover flower shape. And if you want to Google the f orbitals, we don't have a slide for it, but there's 7 of them, and they're also like a flower shape. Very, very interesting to look at them, but same thing, each one of these can hold 2 electrons, and this is just what those shapes look like. So these just happen to have 4 lobes, and then since each orbital can hold 2 electrons, 2 times 5 is 10, that's where we got the 10 electrons in the D sublevel from the earlier slide. And then F, if there's 7 of them, 7 times 2 is 14. That's where the 14 electrons came from the earlier slide. Now, what's new for this week, we're going to talk about the wave nature of light. And this is important because when we understand the fact that light has energy, and if we shine light on an atom and the atom absorbs energy, we can use that information to figure out the electronic nature of the atom. So how the electrons are actually, within the atom. And this is kind of getting into our proof of how we know Bohr was correct. But just kind of, in case you didn't know, I don't know if you've taken physics or not, but light travels through space as a wave. So kind of like an ocean wave. So if you drop a rock in a pond, you'll see little waves. If you have a bathtub full of water and you drop some water into the bathtub, everyone's familiar with the fact that you get little waves going from whatever hit the water. Light is the same thing. Light travels through space as a wave. Now, wavelength is the distance the light wave travels in one cycle. So what we mean by a cycle, going from crest to crest. So the high points, let me draw a nicer one down here. The high points are crests, and then basically we're talking about going from this point to this point. That's what they mean by one cycle, and that's what we would call the wavelength. The frequency is the number of wave cycles in 1 second. So if we have something where there's more cycles compared to, say, this one, we would say this first one that I drew has a higher frequency because I'm squeezing in more of those crests, more of those little bumps in a smaller space. And then this one has a lower frequency because I've got fewer bumps in that space. So frequency, the number of wave cycles or crests per second. Now this number here, this is the speed of light. This is a very important constant of the universe. It's represented by the letter c. So this is the same c as in E equals mc squared. It's the same thing. It's the speed of light. So light traveling through a vacuum, as in outer space, travels this fast. Light traveling through other materials like air or through a diamond or a prism is actually a teensy bit slower. Just kind of a fun fact, but light travels for the most part at a constant speed. And this is important because this number is what relates frequency and wavelength. So we can convert from one to the other by using this number here. So just to kind of relate, because how this is important for in the context of atoms, longer wavelengths will have lower frequencies. So I just alluded to the fact that we can relate these two, wavelength and frequency. I'll give you the equation in just a minute. But longer wavelengths will have lower frequencies, and shorter wavelengths will have higher frequencies. So the equation that relates the two, it looks like this. It's C, and then I'm going to use F for frequency, and then this thing that looks like an upside down Y, that's actually lambda. It's a Greek letter, but we frequently use lambda to represent wavelength. But notice that these two are being multiplied by each other. So, and this C, like we said on the previous slide, it's a constant. It's a fixed number. It's 3 times 10 to the 8th meters per second. Unless we're talking about a unique situation like light traveling through a diamond or something, it's not going to change. So we're assuming that the C is a fixed number. If you have a higher value for the F, then you're going to have a smaller value for the lambda for them to come out, for them to multiply to the same C value. So longer wavelength basically means a bigger number. So longer would mean a bigger number. And then lower obviously means a lower, smaller number. So if wavelength, the lambda, is a bigger number, then the frequency has to be a smaller number, because the two multiplied have to still come up with the same 3 times 10 to the negative 5th, or the negative 8th, I'm sorry. And then this is saying the exact same thing. Shorter the wavelength, so shorter would mean a smaller number. The shorter the wavelength, the higher the frequency, and higher would be a bigger number. Now, how this relates to light, so here they've got an example. They say low energy light, and notice that they're drawing the curve in red, and that's because red light is generally lower energy light, and we've drawn a longer wavelength. So again, wavelength is going from crest to crest, and they're drawing it longer compared to the blue or purple curve that's below. The blue or purple one they're calling high energy light because it is true that blue, violet light is higher energy. This is one reason why we want to wear sunscreen when you go outside, because it's the UV light, UV as in ultraviolet, ultra meaning it's higher than violet, as in it's more energetic than violet. That higher energy light is what can damage your skin. Meanwhile, lower energy light, so we call it infrared, infra meaning below red, that just feels like warmth to your skin. It's not damaging to your skin unless it's obviously too much warmth, like you're burning your skin. But infrared just feels warm. It's infrared. And UV, ultraviolet, is actually damaging to your skin because even though you can't see it, the energy from the light goes right through your skin, or at least the upper layers of your skin, that can cause, skin cancer. And everyone knows this is why we want to wear sunscreen, because we want to protect ourselves from the sun. And then in terms of, wavelength and frequency, so low frequency, smaller numbers, long wavelength, higher numbers, high frequency as in larger numbers, and short wavelength as in smaller numbers. So again, short wavelength, they're going from crest to crest. We've got a smaller distance here. High frequency, if you're looking at the same interval of time, so let's say from this interval of time to this one, here we've got kind of two wavelengths or two cycles that we've crammed in there. And here we've got 1, 2, 3, 4, 5.5. So high frequency meaning we've got more cycles per second. So recall we just said that frequency was per second. So that's the key idea from this slide is wavelength and frequency are inversely proportional. Sorry, can't spell. As one gets larger, the other gets smaller. And then red light is low energy light, and violet light is higher energy light. Now, light that we see from the sun is pretty much a continuous spectrum. And it's not strictly true, but it looks like a continuous spectrum. So if you mix all of the colors in terms of light, not paint, but if you mix all of the colors with light, the light appears white. And for the most part, light from sources like a light bulb, most indoor lighting, it's a continuous spectrum, meaning we're seeing all of the colors. And the visible spectrum is specifically wavelengths going from 400 to 700. And this nm, this is nanometers. Below 400, we're going to have infrared. So those are, I think I actually said it backwards. So below 400, we're going to have shorter wavelengths, so that would be the violet. And then above 700 nanometers, so longer wavelengths, we're going to have the infrared. But the visible spectrum, meaning the colors that we can actually see, that's roughly between 400 to 700. And when we see white light, we're basically seeing all of the colors mixed together. And when you have all of the colors, every single possible wavelength and frequency present, we call that a continuous spectrum. Now, energy, here they're saying radiant energy lower than 400 and greater than 700 cannot be seen by the human eye. That's what we mean by the visible spectrum. So once you get outside the 400 to 700 range, you're talking about other types of wavelengths. So the infrared, microwaves, those are examples of radiation that is, I'll say, less energetic than red. And then when you get on the other side of the spectrum, the infrared, or so the ultraviolet, you have things like X-rays and gamma rays. All of those are more energetic than the violet. But just within this very narrow band of 400 to 700, that's the visible. That's just what our eyes can see. And then what we have in this diagram here, so this is an example of a continuous, so we're going to show what we mean. On the next slide, we're going to have an example of when it's not continuous. But, we've got all the colors here, so it's continuous. And then this is an example. You could do this with if you shine light on a CD. So I don't know how many people use CDs anymore, but if you shine light on a compact disc on a CD and then bounce the light off onto like the ceiling on your wall, you'll be able to see the rainbow. But something similar is kind of what's happening here. But we have light shining through a little slit just to kind of, I'm going to say collimate the light, but then it goes through a prism. And one interesting thing about the prism, so I remember I said the speed of light is a constant. It's the 3 times 10 to the 8th meters per second through the vacuum of space. So basically that's a constant in a vacuum. But if you shine it through something like a prism, it actually slows down. And that's part of the reason why this happens. But the light is being refracted slightly differently. So the point is the colors spread out. And this is one way that we can see rainbows after it rains. The light is shining through the water droplets and the light spreads out through all the different colors. So that's just kind of what we're seeing. The prism basically has the effect of spreading out all the colors so we can see that continuous spectrum. So I alluded to different types of radiation. So I mentioned gamma rays, X-rays, microwaves. Now, all of this together, we're calling the complete radiant energy spectrum. So we've also got cosmic rays and TV and radio waves, but this is a continuous spectrum. And this 400 to 700, it's a little bit arbitrary, but that is just a tiny, tiny band of the electromagnetic spectrum, which we call the visible light. And then here's the ultraviolet that I was talking about and the infrared. So ultraviolet, we get from the sun and that can burn your skin, which is why you want to wear sunscreen. Infrared to our skin essentially just feels like warmth. Microwaves, they are what you think. It's the type of radiation that is used in microwave ovens to heat up water. And then TV and radio waves, so signals meant for your television and meant for your radio are much, much longer wavelength that pretty much passes right through buildings, your body, stuff like that. To an extent, radio waves can't go across the entire planet, but they do have some limitations. But those are longer, very, very low energy, so not harmful. And then on the other side of the spectrum, so beyond ultraviolet, X-rays, like used when the dentist wants to take an X-ray of your teeth, those are those X-rays. Gamma rays also come from the sun, but for the most part, the atmosphere does a decent job of filtering out some of it. And then we've also got cosmic rays from, stars and other celestial bodies that are very, very far away. But all of these are more energetic than ultraviolet. And then all of these are less energetic than the infrared. But the point is that this is a spectrum. So there's no real cutoff between what's considered a gamma ray and what's considered an X-ray if we're talking about something that's, right in the middle. It's a continuous spectrum. And like I said, includes many types of radiation, so I just went through all of those. And pretty much all of these are invisible to the human eye. It's only this very, very, very tiny portion that our eyes are sensitive to. The rods and cones in your eyes are sensitive to only the radiation that's in the narrow band, which we call the visible part of the spectrum. Now, we talked about the word quantized, so kind of to clarify what that means, and then we're going to bring it all together and say, well, how does this relate to the atom? So the quantum concept states that energy is present in small, discrete bundles, meaning you have one packet of energy, or 2 packets of energy, or 3 packets of energy. You can't have 3.5 packets of energy. This can be applied to almost anything you can think of. So my favorite analogy is students in a classroom. I might say students in a classroom are quantized. I can have 2 students, I can have 10 students, I can have 20 students. I hope I don't have 18.5 students because that would be a little bit bloody and gross. So you could say students are quantized. Anything that you can count where you're not, you can't really split it up, we could say that's quantized. With regards to energy, which is really what we mean when we say quantized, we're talking about bundles or packets of energy, so fixed amounts of energy. The analogy that the book has, so a ball rolling down a ramp, it's losing energy continuously, but if it's bouncing down the stairs, it's losing energy in quantized packets because it loses so much potential energy going to one stair, and then it loses a little bit more potential energy going to the next stair. So this kind of requires a little bit of physics knowledge where, as things, as a ball or any object gets closer to the surface of the earth, it's losing gravitational potential energy. And I don't know if you guys have taken physics at all, but the staircase analogy, this is the idea of, again, something being quantized because it's only so many stairs. The ball is not going to fall down 3.5 stairs. It's either going to go down 3 stairs or 4 stairs or 5 stairs and so on. Meanwhile, if we have a ramp, it can roll so far down the ramp and stop at any point along this ramp. So then how does this relate to atoms? So one thing that we've noticed, if we excite, so we've got hydrogen here, if we excite hydrogen gas, and then the light that's emitted, if we do the same thing as we saw earlier, we shine that light through a slit and through a prism, the colors get spread out, but we only see certain colors, which we thought was kind of strange. Why do we only see these 3 colors when we shine the light from a hydrogen lamp through a prism like this? So the reason is because the light, or the electrons in the atom are quantized. They can only be on level 1 or level 2 or level 3, and this is where it all ties together. But we're calling this type of spectrum, so before we called it a continuous spectrum, this one we're calling an emission line spectrum because what's happening is the light is being emitted from the hydrogen gas, so that's the emission part. Line, because we're seeing very specific lines from the spectrum. Now, each element has its own unique signature or fingerprint, if you will. So this is what hydrogen happens to look like. It's a very simple spectrum, and elements that are higher on the periodic table, like bromine or iodine. So I just mentioned two halogens, so remember you have to learn the names of the different columns. So bromine and iodine, they're more complex, they have more electrons. Those electrons are on more energy levels and sublevels. They're going to have many, many more lines. Hydrogen is the simplest, smallest element on the periodic table. It has a very, very simple emission line spectrum. So tying back to the atom, what Bohr figured out that this business about emission line spectrums and the fact that we were only seeing very specific colors was the evidence that he needed to explain his theory about having specific energy levels. So what's really happening, so here's the red, we said that red was a lower energy. So we're showing, they've got a little arrow here going from level 3 to level 2. What they're saying is when an electron, if an electron that's on level 3, if it should fall down to level 2, it's going to emit a little bit of light. So light will actually leave the atom if an electron goes from this higher energy state to a lower energy state. And the wavelength of this light happens to correspond with red light. So next, they've got blue-green. They're showing blue-green going from 4 to 2. So what that means is imagine an electron that's living on level 4. If that electron were to fall down to level 2 for some reason, it's falling from a higher energy state or higher energy level to a lower energy level, one that's closer to the nucleus. When it falls like that, it's going to emit some light. And unfortunately, I can't change my color pen, but it's still going to emit some light. And the wavelength of that light just happens to correspond to blue-green according to our eyes. And then violet, they're showing it going from level 5 to level 2. What that means is if you had an electron on level 5 for some reason, and it fell down to level 2, so it's going from a higher energy to a lower energy, the light that it gives off when it falls like that happens to look like violet color to our eyes. So these transitions going from higher energy levels to lower energy levels, that happens, obviously they can only happen if the electron gets up to that higher energy level in the first place. Now we learned, hydrogen only has one electron, and that one electron is going to be living on level 1. So how could an electron get up to these higher levels in the first place? Well, here it is. So in our diagram, we're talking about an excitation voltage. So we're putting energy in to these hydrogen atoms. We're pumping them full of energy, and when we pump them full of energy, we're basically promoting electrons up from level 1 up to these higher energy levels. And then when the electrons fall back down, that's when they give off the light. And this is essentially how neon lights work. We excite the atoms, the gas that's inside the light bulb. The electrons that are in those atoms absorb that energy and jump up to higher energy levels. And when they fall back down, they give off light. So we're putting in electrical energy and they're giving off light energy. And then which color we get, it depends on the element that is in the tube. So I talked about how each element will have its own unique spectrum, and we call it basically an atomic fingerprint. So the emission line spectrum of each element is unique. So we had hydrogen on the previous slide, helium, the next element on the periodic table, just slightly more complex. It's got eight different lines. At least these are 8 different lines that are in the visible spectrum. You can imagine looking at hydrogen, we could have more possibilities. Like what if we had an electron going from level 2 down to level 1? We didn't talk about that. That's because this transition, although certainly possible, doesn't appear in the visible spectrum, so that's why it's not in our example here. That one would be a lower energy transition going from level 2 to level 1. So this would be a low energy, so something that's like in the infrared. You could also theorize, what if we had something all the way from level 7 going down to level 1? Well, that's a huge energy transition. So that's high energy. That would be something, certainly possible, but that energy, that high energy transition is going to correspond to a wavelength that our eyes cannot see. So that's why we didn't put it in our visible spectrum here. That would be something that's UV or maybe even more energetic than that. So what we're seeing with these emission line spectra for these 4 examples, these are just the lines that happen to be in the visible spectrum. And the point is that it's unique. Every single element has a unique atomic fingerprint. If we excite a sample of gas, so if you have sodium as a gas, and sodium, which hopefully it's a metal, and metals are usually solid at room temperature, but if you had gaseous sodium atoms and you excited them with electrical energy, and then when those electrons fall back down, you get these 2 lines that happen to be in the visible spectrum. And this, where it's got 2 yellow lines, that's unique to sodium. And again, we call that the atomic fingerprint. This is one thing that we can use to identify what elements are in stars. So if you are interested in astronomy, how do we know what elements are in stars that are very far away? We look at the light coming from those stars, and we pay close attention to what atomic fingerprints we notice are coming from those stars, and that's how we know what elements are present. That's how we know that our star has a lot of hydrogen and helium, for example. So the next thing in this video, we're going to transition over to electron configurations. So I had this slide last week. We could use a periodic table to predict which sublevel is being filled by a particular element. So we talked about how this block of the periodic table is called the S block. And then we talked about the transition metals. So this block in the middle is called the D block. In green over here, this is the P block. And then down here for the lanthanides and actinides, this is the F block. So when we write electron configurations, and I'm going to teach you the way that I recommend. There are other tricks to write electron configurations, but I'm going to show you what I call the walking across the table method. It's a very, very common method, and it's my preferred method, but we're going to use the fact that this block is the P block, this is the D, this is the P, and this is the F, and that's going to help us write our electron configurations. So they've got the orders in here. They say 1s, 2s, 2p, but where did that order come from? So if you were to start, so this is kind of like our starting point. This is essentially hydrogen. Writing an electron configuration is essentially filling out the order that electrons fill. So when we talked about the Bohr model of the atom, here's our nucleus. We had level 1 is first, and then level 2, and then level 3, and so on. When electrons are added to atoms, if you will, we're always going to start with the lowest energy first. And the lowest energy is what's closest to the nucleus. So writing out the electron configuration is basically writing out the electrons in the order from lowest energy to highest energy. Closest to the nucleus to furthest away. Now, if we're going to, let's say this is our target. This just happens to be chlorine on the periodic table. They don't have it labeled here. But if we wanted to write the electron configuration for chlorine, so listing off all the electrons that are in the chlorine atom from lowest energy to highest energy, we're going to start in the upper left, and we're going to walk across the periodic table. So I've got an electron in the 1s, and then going this way, I have another electron in the 1s, and then we're going to loop around and go basically kind of reading the words in the book. We go from left to right, top to bottom. Then we go over to the 2, and then we've got 2 for 2s right here, and then you go across, and then we get to 2p, and then we go across, looping around, and then we get to 3s, and then keep on going. And then if we're going to do chlorine, we next do the 3p, but we only go in 5 units. So we're going to put this all together, but that's what I mean by this walking across the periodic table thing. We're basically going from left to right, row by row, top to bottom. And that's basically how we get the order. So the 1s came first when we did that walking across the periodic table exercise, and then 2s came next, and then 2p came next, and then 3s, and then 3p. And if we kept on going, we would find that 4s comes next, and 3d, and so on and so forth. So that's how we get this order. Now for each sublevel with electrons, fill each sublevel with electrons until you have used all the electrons in the atom. So they're basically talking about these little numbers here. So these superscript numbers that we have here, that's referring to how many electrons are in that particular sub-level. And then notice that we said s orbitals can hold 2. So we've got a 2 right there. Here's another s where there's 2. We said that p orbitals, when you have the 3 of them together, the p subshell can hold 6 because each little orbital can hold 2, and 2 times 3 is 6. Here's another 2 for the s, and so on. That's what they're talking about. These superscripts are the number of electrons, and it makes sense. It corresponds to what we said, how many electrons a sublevel can hold. Now, they did an example for bromine. Bromine is just below chlorine on the periodic table. It's over here. And then if you look at your periodic table, you'll notice that bromine has an atomic number of 35. That tells you that it has 35 protons, which also means it has 35 electrons. So that's why they have 35 right here. And all of these superscript numbers should add up to 35 to indicate that there are 35 electrons. And the 1s would be the lowest energy, closest to the nucleus. And the 4p over here, these 5 electrons in this 4p subshell, those are the ones that are furthest away from the nucleus. And again, kind of review from last week, why do we care about all this? These are the valence electrons. So valence electrons are the ones used in bonding. All of these other electrons, these are core electrons. So we care about this because we really want to know how many electrons and which electrons are the valence electrons, because valence electrons participate in bonding. Bonding tells us what type of compound we're making, what the formula is, the name is, and then that ultimately tells us what the molecule can look like and its physical properties and chemical properties. So this all builds upon itself. The electron configurations can be fun to practice, at least in my experience, the students find them fun. But, this does have a purpose. But basically, we're looking at the valence electrons, like the ones that you write last, those are the valence. Those are the important ones. So we're going to do a few examples. They've got sodium right here, but I'll do a few more. So sodium, and actually I'm going to switch over to a periodic table I can write on. So here's sodium. Here's sodium on the periodic table. And if we want to write the electron configuration for sodium, again, we're going to start in the upper left corner. And again, this is the S block. This, the transition metals here, that's the D block. This is the P block, and then down here, this is the F block. So we have S, D, and P. So if we start in the upper left corner, this first block, this is a 1s. 1 because it's on the first level, so this is level 1, 2, 3, 4, 5, 6, 7. And then this one over here, this is also 1s. So there's 2 blocks, if you will, or 2 elements that are on the 1s. So we'd start off with 1s2. So the little superscript 2 for 2 electrons. Next, wrapping around, we come over to level 2. So again, top to bottom, left to right, kind of like reading words on a page. We've got 2 right here in the 2s block. So we're going to have 2s2. So the big 2 is saying we're kind of like on row 2, s, because it's in the s block. And then the superscript 2, because there were 2 of them in the s block, so 2 electrons. Next, we keep on going. So next, we're entering the p block. We're still on level 2, but now we're in the p block. So we're still on level 2, but now we're on the p block. We haven't actually arrived at sodium yet, and there's 1, 2, 3, 4, 5, 6 spaces here, if you will, so I'll write a 6, 2p6. Keep on going. Now next we get to level 3, and then this is in the p block, the s block, so I'll write s, but we've reached sodium. We only needed 1 space to get to sodium, so we're going to write 3s1. If we wanted to write the electron configuration for magnesium, the next element, then we'd be talking about 2 right here in the S block, so then this would be a 3s2 if they asked for magnesium. So that's why they say 1s2, 2s2, 2p6, and then 3s1, because there's only one valence electron for sodium. So again, this kind of matches up with what we told you to memorize in earlier weeks. Elements in the first column have one valence electron. Elements in the second column have 2 valence electrons. Elements in this column have 3 valence electrons. That's where it comes from. When you're writing your electron configuration, the electrons that are furthest away from the nucleus, those are our valence. Valence as in they're furthest away, and then valence as in they participate in chemical bonding. So I'm going to try to erase, and we can do another example. So let's do aluminum. Aluminum is a good example. So here's aluminum. We're going to write the electron configuration for aluminum using the same walking across the periodic table method. So we're going to start up here. So this is like 1s1, 1s2. So I'm just going to write 1s2. So then wrapping around to level 2, this is the S block, and there's 2 electrons here. There's 2 elements there, so we'll write 2s2. And then next we get to this section, which is still the second level, but now we're in the P block. So 2p, and there's 6 elements here, like six spaces, if you will. So 2p6. Then we get to the next level. Now we're on level 3. This is the S block over here, so I'll write 3s, and there were 2 elements here, so 3s2. And then next, keep on going. Now we're still on level 3, but now we're in the P block, and aluminum is only 1 in, as you will, so we'll just write 3p1. And then that's it, because we've reached aluminum. As we were walking across the table, we just keep on walking until we get to the element that we're trying to write the electron configuration for. Let's do one more practice example. We'll do one that's a little trickier. So I'll do this one. I'll just go in blue. So let's do like iron, for example. So this is going to be our target. We're going to write the electron configuration for iron. So again, we start up here. So these two together give us 1s2 because they're both on the first. Helium's technically, you could think of it right here, but we talked about this earlier, we put helium with the noble gases because it behaves like a noble gas, but in terms of electron configurations, it's kind of like it lives over here. So 1s2 is, we always start with 1s2 for all of them, if you haven't noticed already. Next, wrapping around, come over to level 2, so 2, and then this is the S block, and there's 2 electrons, so 2s2. Next, we come over here, so this is 2p6 because it's level 2. It's in the P block, and there's 6 of them here, so 2p6. Then we come over to level 3. This is the S block, and there's 2 of them there, so 3s2. And then we keep on going. Now we're still on level 3, but now we've moved over into the P block. So 3p, and again it's 6. There's 6, we're doing the whole thing because we haven't gotten to iron yet. So 3p6. Keep on going. Now we're going to come on over to level 4. Now these first 2 are in the S block, and there's 2 of them, so 4s2. Next, when we keep on going, so we go over to scandium. Now we're in the D block. We're still on level 4, but now we're in the D block. And let's count. 1, 2, 3, 4, 5, 6 to get to iron. So we're going to end with 4d6. That's how you write the electron configuration for iron. And you can practice this with just about any element. Now, one resource that I'd recommend is ptable.com because it's a nice way. It's basically a dynamic interactive periodic table, but you can practice your electron configurations. Pick any element, try your best to write the electron configuration, and you can use ptable.com to sort of check your work. Now, the last thing, it's kind of optional, but it's optional in terms of the course, but it's a pretty easy concept, I think, because what if you had to write the electron configuration for an ion? So recall an ion, whether you're talking about a cation ion or an anion. An ion is a charged particle, essentially. So here we've got sodium. If sodium was to become an ion, it's a metal. Metals like to lose electrons and become positively charged. So that's why we have a sodium with a little plus sign over here to represent that it has lost one electron. So it's deficient by one electron. Recall that protons are positive, electrons are negative. If it's lost a single negative electron, it has excess positive charge. And if it loses one electron, so this one, then it's going to have a charge of +1. What happens to the electron configuration? So here's the full electron configuration for the neutral sodium atom, but once it becomes an ion, look what's missing. It's that valence electron that was lost. It's the 3s electron that's now missing. So this would be the electron configuration for the sodium ion. It's basically lost its valence electrons. Now, nonmetal, so oxygen, recall that nonmetals like oxygen, nitrogen, carbon, so those elements on the right side of the periodic table, they like to gain electrons to have a complete outer shell, an octet. Oxygen in particular likes to gain 2. Electrons are negatively charged, protons are positive, so an oxygen with a 2- means it has an extra 2 electrons, and that's why we have O with a 2-. What happens to the electron configuration? So this is for neutral oxygen using the same method that we just used. You'll end up with 2p4 because oxygen is 4 elements in. Here's your oxygen. It's 4 elements in the p block. But once it gains those 2 electrons, look at the periodic table. So if it has 4 and then it gains 2 more, now it's kind of like neon. We say it's isoelectronic with neon. It has the same number of electrons that neon would theoretically have, which is now 6. So that's why this has changed from 2p4 to 2p6. And then remember we talked about the octet rule. Notice that we've got 2s2 and 2p6. 2 plus 6 is 8. 8 as in octet. So what's happened in both of these cases, the outer shell is now 8 electrons. So sodium, the outer shell is no longer the third, it's now become the second because it lost that electron in level 3. Now we've got 8 electrons in the new outermost shell. Same thing has happened to oxygen. Oxygen now has 8 electrons in its outermost shell. It now has a complete octet. So that's how you would write the electron configuration for an ion if you had to. It's a very, very similar thing. You just imagine how many electrons does it have now that it's an ion, and how would that change its configuration? And it's just adding or subtracting electrons accordingly.